Welcome back, guys. So in the previous video, we established that we use functions to actually describe what goes on in real life, things like the algebraic expressions, all those algebraic expressions that we learned about, whether it's a monomial, it's a binomial, it's a trinomial, or any kind of polynomial really can actually be represented on the Cartesian plane. And for us to be able to represent that on a Cartesian plane, we must represent it in a form of a function. In other words, in a form of a rule that tells us if you input a certain x value, you're gonna get a certain y value. In this case, as you can see, we had the rule that says y equals to 2x minus 3. In other words, to get y values, you must take an x value, multiply it by 2, and subtract 3. That's what we'll get. And we represented this on the Cartesian plane. We saw that it is actually a straight line. It is actually a straight line. Now, I want us guys to start off by looking at the properties of this straight line function. If you may say so. Yes, a straight line is a function. Sometimes we call it a linear function. So I want us to look at the properties. The first property that we are going to look at, and I'm glad that we have discussed analytical geometry by now, is the fact that this function here actually has what we call a gradient. Now, to quickly find the gradient, we're going to use these 2 points here, A and B. They are on the line. So if you remember our definition of a gradient, it is changing y, why do I write x there, over changing x. And so what I'm going to do, I'm going to look for the gradient of this line, and I'm using points A, B. We can see that it is going to be minus 3, right? Minus 0. I'm starting at A, going to B, and then over 0 minus 1.5, excuse me. And we see that this is now a minus 3 divided by a minus, or a negative rather, that's correct word to use, negative 1.5. And you can just punch this in the calculator and say 3 divided by 1.5, you will get an answer of 2. So the interesting thing, guys, here, I want you to now start seeing the relationship between your analytical geometry and your algebra and now functions. Look at this now. Using analytical geometry, we were able to prove that the gradient of this line is indeed 2, as we have there. So if you look at it, the general form of a function, okay? We can come up with a general form of a function here. The general form of a function then is as follows. Allow me to just clear up. Let me see. Y equals to 2x minus 3. We have established that this thing here is the gradient. That's what we have found. Now, I want you to think a little bit with me. I had said this is the x-intercept, and I had said this is the y-intercept. Now check what we have here on the y-intercept. X is 0, y is minus 3. Where is minus 3 on our graph or on the equation? Here is minus 3 or negative 3. So we can see another thing actually, and this makes sense algebraically. If I say y equals to 2 and I substitute a 0 there and I have a minus 3, indeed I get the fact that y is a negative 3. So that's why we call it a y-intercept, because the x-coordinate is actually 0 at that point. Let us see if we can get 1.5 if we set y to be 0. If I set y to be 0, then 0 is equal to 2x minus 3. So 2x equals to 3. And so x is 3 over 2, and this is exactly 1.5. So we see something very interesting here. that with the linear function, I must be specific now here, we are actually discussing the linear function, which we have seen is just a description of words in a real life situation. So we see that in a linear function, here's an important thing. You will have an x-intercept and a y-intercept, not always, by the way, okay? But you will have that, okay? As a matter of fact, I should actually, for you in grade 10, you are always, may I say again, you are always going to have x and y intercepts because we are introducing you. So you are guaranteed you are always going to have to look for the x-intercept and the y-intercept, all right? Now, finally, let us now look at another concept of the domain and the range of this function. Okay, we have diagnosed it now. We have established this is the gradient, this is the y-intercept. Now, let us try and look at the idea of the range and the domain. When we talk about domain, guys, we are looking at the set of x values on the x-axis, for which our function, as we know it, y equals to 2x minus 3, will be defined. Okay. In other words, if we go through the Cartesian plane and we look at our set of x and y values, I mean x values in this case, will we get an answer for the y value? Algebraically, we can see as long as x is a real number, or whether you're going to move from infinity to infinity, you will always have a corresponding y value. That's what we see. So when we look at the domain, we are saying, okay, for which x values is this function defined? And in this case, we can see for a straight line, all x values, as long as x is a real number, for every x value, there will be a corresponding y value. Any x value, there will be a corresponding y value. Range, guys, refers to the set of values that you get as a result of the x values that you put in. Okay? So range, meaning we're going to look at the y-axis now for the range. So we check if the graph is defined, if the graph exists for all values of y. And for the straight line function, indeed, we can see that yes, y will be any real number. In other words, for any real number that you put in here, you will get a real number also. And so these are the two ways we can express, okay? These are the two ways we can express the domain or the range for a straight line graph, or for a linear, if I may say, for a linear function. These are the two ways. Guys, I'd like to leave it here for now. I hope you can digest this and make sense out of it. Cheers.